Metamorphic rock. Back again. Get your flowchart out, and I want you to go and watch Michael Samaranto's video on metamorphic rock. Meta means change, morph means form, so change in form is what metamorphic means. What's that one? Oh, yep, that link is there, I think. So go and have a look at that one. That should be in order, so it's whatever was after that one there. Apologies if it's not there. So they form when any of the rock types are exposed to temperature and pressure, so increased temperature and pressure. Increased temperature means that the elements can move around and so reform other crystals, and basically enough pressure, because minerals take up a different amount of space from each other. So some minerals, think about ice, how ice is less dense than water because of its crystal structure. Pretty much everything else is the opposite, but that gives you an idea of a mineral having a different density. So ice is less dense than water, and water's about, granite's about 3 times as dense as water, so ice is far less dense than water. So, and that's because of the minerals in granite being denser. So some minerals are denser than others. So what happens is, well, they take up less space. So when pressure is there, what the rock wants is forced to do is to have denser minerals in it because they take up less space because it's being squashed. Increased temperature helps that happen. So new minerals form and it changes the physical structure as well. So 2 types of metamorphism: regional metamorphism and contact metamorphism. Dynamic's a 3rd type of metamorphism, but we're not going to worry about that. Regional metamorphism is on a really large scale, so it can be like thousands of kilometers long, and so pressure and heat through plate tectonic movement. So the Earth's surface crust is made of a number of tectonic plates which crash into each other all the time. Contact metamorphism, on the other hand, it's heat through contact with magma or heated fluid, and it's localized. So every here and there on the planet, actually, yeah, a lot more than every here and there, but anyway, magma will be coming through the crust, and as that magma comes through the crust, it's in contact with the crustal rocks. Now those crustal rocks get heated up, and because of that heating and a little bit of pressure there, but mostly because of the really hot magma coming through, it changes, because some minerals also melt at lower temperatures than others. So if the magma is hotter than a particular mineral's melting point, it will melt. And it could go into the magma, but if it's too far away from the heat source to go into the magma, it'll form another mineral. Because it's not always right next to it. It could be kilometers away from the magma, and still the heat would get to it over a long enough period of time. Okay, so like igneous rocks, they are hard and strong, yet they are brittle. They also will snap. They often have foliation due to the pressure, and sometimes have gemstones. So here's a ruby and some marble. Lots of little gemstones in this eclogite. So there's little minerals in this one. This is called a gneiss. And we can see the banding in this one, can't we? So if you're down the southwest of Western Australia, go out to the Gap and you'll see lots of this sort of stuff. All the way in Torndirrup National Park. Well, pretty much all the rocks around this place. So lots of gneiss everywhere. So lots of little gemstones in that one. So there's some foliation. So it's not like layers, it's different to layers. Sedimentary rocks have layers, but we can see that different minerals are lining up, as opposed to sedimentary layers just have layers. You can't really see it in the minerals themselves, unless the sedimentary rock's been exposed to heat and pressure. But the thing is, then we call it so shale is still a sedimentary rock, but when it becomes slate, it becomes a metamorphic rock, and slate, you can definitely see foliation in it. Just like when we looked at the igneous rocks one. This isn't something you're going to need to know, but it's good to understand what we're looking at. Not on this planet. So here we have temperatures of up to 1,000 degrees. So that's only coming from magma or coming from depth. Zeolite, I'm not going to worry too much about that or this one. But schist. So schist forms under a fair amount of pressure. Blue schist and green schist, that's just slightly different minerals. Amphibolite, granulite. Now gneiss is somewhere here, and we can see eclogite is up there. Different temperature and pressure means different metamorphic rocks are going to form. If you find a granulite, you know that where you found it must have been exposed to really high temperatures. So if you find a gneiss is really high temperature metamorphic rock, it's high grade. Whereas if you find a schist, you know that, yeah, a reasonable amount of heat, but nowhere near as much, so it's a lower grade metamorphic rock. So in Cooma in New South Wales, there was magma that came through the crust. So we're moving towards the heat source. So we can see that there's sandstone here, and then we move closer to the heat source, and we start to get this unusual banding coming through, which eventually forms a schist. So even closer, and then we got closer, and it comes out of the foliated, shiny mica schist. So not as nice. And then we get to a not as nice. So this is nice, and we can see that definite banding in the gneiss. Had a rough life, this one. A lot of stress on that rock. So gneiss is a higher grade. So this gneiss was closest to the heat source. This sandstone was furthest away, but this gneiss originally was sandstone. Before the magma came up through the crust and cooked it and heated it up, it was a sandstone. And then over time, so further away from the heat you get, the lower the grade of metamorphism. The heat source for the metamorphism actually came from a plume of magma which pushed its way up from the mantle and through the crust. Now when it got to the surface, because it made it the whole way through, the rock that came out of the magma was basalt, and this is actually a sample from the basalt, which was the heat source. We can see that there's a little bit of green in it. Now that bit of green is actually a bit of mantle that was picked up as it moved through the mantle, and then was brought all the way to the surface. Now that mantle rock has a really high melting temperature, so that actually wasn't hot enough to melt it. So that's pretty interesting. So increasing temperature mostly, and some pressure, increasing metamorphic grade. So we've got phyllite, schist, and gneiss. So this is a high grade, this is a low grade metamorphic rock. Eclogite is a metamorphic rock that it looks igneous because it's got these big crystals in it, but it is metamorphic. It forms about 100 kilometers deep in the earth. What happens is oceanic crust. Basalt is mostly basalt, and basalt ends up through plate tectonics, it ends up deep in the earth. And so when the basalt gets deep in the earth, it cooks and rearranges to form eclogites. That's pretty cool. And marble, if you cook a limestone, if you heat it up a lot, it makes marble. Oh, this one's cool. It's a metamorphic rock, but it's hard to say it forms by natural means because an atomic bomb blast, so the pressure and heat associated with an atomic bomb blast forms this really glassy metamorphic rock, because obviously it all melts really quick and then freezes really fast, so we get a glassy sort of stuff. So that only happens. And there's a few other things that can form when asteroids hit us, but not this particular one. We get something called shocked quartz. Probably some other things when asteroids hit us. Little side note, that's how we know where asteroids have hit us, because we find this stuff called shocked quartz. It's quartz that's just been ruined, and quartz is a pretty tough mineral. It's been put under extreme stress. Okay, you can watch Nick on the Rocks. So he talks about columns of basalt, so those basalt pillars. Hopefully you like Nick on the Rocks. He's quite endearing in his enthusiasm. And you can look up one of drone footage of Icelandic lava river. You can look up that if you want. It's pretty good.